Please be welcome to the Chemical Engineering Seminar. Today we have Dr. Stuart Coles. He's a reader of Sustainable Materials and Manufacturing at the WMG, University of Warwick, UK. His main research interests are geared towards the use of waste, recycled, and bio-based materials into commercial products and processes, and understanding the overall environmental impact of those actions. Most recently, Dr. Coles has been leading research on recycled carbon fibers in composite applications. Studies have been conducted on the application of recycled carbon fibers in thermoplastic and thermoset resins, aiming to understand the structural processing property relationships of these materials. Alternative composite materials also has been investigated, including the use of waste cooking oil as a feedstock for the synthesis of bio-based epoxy resins, and their use within energy absorption structures. These resins have been successfully combined with carbon, glass, and flax fibers. The use of recycled carbon fibers has also been extended to the production of hydrogen through the microbial electrolysis cells. Additionally, Dr. Coles looks at furthering our understanding the environmental impact of our actions and how they might affect our decisions making in the future. He has led research into developing sustainability assessments through the use of multi-criteria decision analysis, as well as developing full life cycle models for the lithium-ion battery manufacturing and the chemical recycling of polymers, both of which continue as active projects today. Please be welcome Dr. Stuart Coles. He presents the seminar, Avoiding the Fatberg, Turning Waste Oil into Polymers and Composites. Welcome.
Thank you. Thank you for the very kind introduction. And I'm really pleased to have the invitation. So thank you very much for allowing me to talk to you all this afternoon or evening, as it is here. Very dark outside, so hopefully it's much better where you are. I'm going to talk about this seminar about avoiding the Fatberg, and it does relate to our work on waste oil, turning that into polymers and composites. And I'll talk to you a little bit about the process, some of the problems that we experienced along the way, some of the results that we found, and kind of go through that whole process of how we got to those impact structures that were mentioned just a moment ago. Just going to get this. There we go. So this is a map of the UK, just to make sure you know where I'm from. This is what our little island in the middle of the Atlantic looks like. And just as a point of note, the University of Warwick isn't in Warwick. Warwick isn't even the third closest place to the university. We're actually based right on the edge of Coventry. Campus actually sits on the boundary of Coventry and Warwickshire, so we're kind of located here. It's great for central location because we're really close to Birmingham Airport. It's only about 20 minutes from campus, and then obviously Coventry itself is very centrally located within the UK, so it's a great location to work in, and particularly for us within our department, right in the middle of the automotive industry. Lots of OEMs and manufacturers, tier 1, tier 2 suppliers, all in the area. So it's a really good area to be working in. This is a nice picture of campus. It doesn't always look as nice, but I always like to show this as well to say that the UK does have some nice weather at some points. It hasn't been photoshopped, and is a really nice place to come and visit. We in the Sustainable Materials group have now been based at WMG for many years. I've been part of the group for 15 years now, working in this sort of sustainability field, and we do a lot of different things within the group, which was kind of illustrated by the introduction. The overarching theme is that we try and develop sustainable materials and manufacturing processes. So as long as it's using waste, recycled, bio-based materials, and that's where we really like to sit. If it relies on fossil-based materials, then that kind of moves us out of the area. But we do lots of work with industry. WMG as a department is very much an applied research department, so we work closely with industry in lots of different areas. Things like battery manufacturing, chemical recycling, composites, wastewater treatment, all of which are kind of mentioned and summarized in some of the papers below. And if you're interested in any of the work there, the links are all there for you to go and have a look at, because there is quite a variety. This talk seminar is going to really focus on the polymer processing and the bio-based materials that we've been working on over the past few years, and in order to sort of generate some of these composite materials. So we start off with vegetable oil as a renewable feedstock. We know we can get vegetable oil everywhere, particularly in the UK. It's a crop that grows really well. Rapeseed oil, particularly during the spring and summer months, you can see lots of bright yellow fields up and down the country. So there's lots and lots of vegetable oil that's around. Very easy, cheap source of feedstock. There is potential conflict maybe with using a food source material for non-food uses, but we have some information that suggests, certainly from work done by the World Bank, that perhaps the conflict between food and non-food use isn't as stark as people would like to think. So, but it does cause us a problem, and we'll refer back to it in a moment. But we know we've got vegetable oil, and we can epoxidize it as well to create a material called epoxidized vegetable oil, which is a very large industrial chemical, well over 200,000 tons a year. Typically, it's mostly used as a plasticizer for polyvinyl chloride, and sometimes as well, it's a reactive diluent in epoxy resins. Only not so widely there. The vast majority is as kind of a plasticizer for PVC. So we know that vegetable oils are plasticizers. We know that we can use them on industrial scale quantities, and that they're quite a versatile material. That functionality, once it's epoxidized, you can do lots of different chemistry with that. Change it from epoxides to ring opened alcohols, or you can ring open a variety of different Lewis acids that will, in order to give you those different sort of functionalized structures. Triglycerides generally look like this. We have like the three arms. This is what it would look like when it's epoxidized. So you've got these epoxide groups there. As I say, they can be ring opened, moved around, changed as and when. Now, ideally, what we would like to do within the automotive space, certainly from my perspective as from an academic in the area, we want to increase the amount of bio-based material within these applications. We want to reduce our reliance on fossil-based materials. But the problem with doing this is that the materials themselves aren't necessarily economically competitive. Often the weight or the performance or the cost gets in the way, and there become some real challenges in using these materials. We have additional insecurities in the food supply chain, plus concerns about that food versus non-food usage. And so because of these kind of two key factors, what we thought was that what we should really try to do is avoid using a food-based material. Is there a more sustainable, more affordable oil source that we can access that would allow us something that at least reduces some of these barriers? And we started to come across the problem of Fatbergs. Now, these are effectively very large lumps of fat and solid waste and grease that just congeal and solidify within sewer systems. And within the UK, it's estimated that around 70% of all of the blockages that you find in sewers are caused by these Fatbergs. And it's not only just the oil, but sometimes you get wet wipes from babies and nappies and other such things. Anything sort of solid that goes down the toilet congeals with the oils, and in the cold temperatures, particularly in the UK, when you can get well below freezing during the winter, it does make it very difficult for these materials to stay liquid, so they solidify and then they congeal. The image here is one that is a picture of one that was 64 meters long, that was found in Devon, which is in the southwest of the UK. Probably the more famous one was the one that was entitled #Fatberg. And that weighed 130 tons and was the length of 2 football pitches, and found in London in the sewer systems there. And it took nearly a week of intense work and road closures to clear that out. So there was a huge disruption and economic cost and problem from getting rid of this blockage in the sewer system, which in the UK is quite antiquated now. So this was clearly a problem, but waste oil, fats and greases are ending up in the sewer system. So we want to avoid that and find a different use for our waste oils. Now, quite a lot of the time at the moment, waste oils will be used to make biodiesel. So you'll take your waste oil, turn it into biodiesel, and run a truck or a tractor or a car or whatever it might be on it. The issue with that is, in the long term, diesel engines are going to be phased out. So we need to think about what options we have outside of that diesel space. Plus, the quality of the diesel fuel that you get from it isn't quite as good as what is conventionally there at the moment, and certainly not good enough for some of the more high power, high demand applications. So we need to find something different to do than biodiesel. We need to find something different to do than throw all this waste down the sink and just deal with it in the sewer system and water treatment plants. And that's where we came up with the idea of, well, could we use the waste oil as a chemical feedstock for some of our processes that we were looking to develop, instead of using the virgin vegetable oil? So we get our non-edible and abundant source of triglycerides. We have a societal factor because we're reducing the blockages in the sewer system. It also helps tackle some of the oxygen depletion that you get in the water, because the fats don't cover the surface of the water. We're not having people effectively try to reuse it as another feedstock for the food system. And we also get something that is economically cheaper than virgin oil and reduces costs of effluent treatment, and it reduces costs of economic of dealing with the waste, digging up roads, all of this kind of associated solving the problem after it's been all broken down. And so that to us meant that we were finding something that we could at least claim was a more sustainable source than what we'd done previously. So that became our starting point. But obviously, this waste vegetable oil was waste. It had been cooked with. And one of the first challenges that we needed to find was understanding what was going on to the oil before we got to it. And actually, when you're sort of deep frying and the sort of traditional processes that you would use cooking oil for, particularly in restaurants and large-scale food preparation, oil's largely used in kind of deep frying, and that in itself is quite a complex chemical event when you look into what's going on in there. You've got degradation processes that are happening to the oil, so things like hydrolysis, because there's still water in there, and particularly the food that when you drop in there adds water to the system. You've got thermal oxidation of the triglyceride. You've got potential polymerization of some of the chains to make oligomers and dimers, trimers, etc. All of this effectively reduces the degree of functionality that you have within that oil. So we started off with the oil having a nice versatile feedstock, but we know that through the cooking process that we were going to start to reduce that level of functionality. And one of our first challenges was to understand how much was that functionality going to be reduced, and whether we could mitigate it in any way, or was it actually going to be a problem in the first place? So we've got a number of processes here, but we're kind of looking at how much do we maintain as kind of triglycerides, how much are we getting as monodi and free diglycerides, free fatty acids, are we getting sort of dimers and trimers, epoxies, are we ring opening those with alcohols, and are there any other sort of thermally degraded species that are in there as well? So our first step was to just purify it and do some simple purification and epoxidation steps. And the purification step, we literally stripped straight from biodiesel production. It was exactly the same process that we used there. So you take the waste oil, effectively filter it to remove out any of the lumps of burnt food and debris that are in the oil, and then add a very small amount of water. If you add too much water, you start to have the potential to produce soap, so you keep that down to a very minimum, but you do a small amount of water quite a few times in order to remove the sort of polar compounds that you've got. Maybe some of even like the monoglyceride, some of the sort of more water soluble materials, they all come out in that sort of purification step. And what you're left with is a vaguely clean triglyceride material. Not perfectly clean, but it is certainly a lot cleaner than it was before doing that step. From there, we knew that there was still some double bonds in those materials, so that gave us the door opening to allow us to get in there and do some functionalization with these materials. We tried a number of different routes with acetic acid and a little bit of sulfuric acid. We also tried a more traditional organic chemistry route with using MCPBA and chloroform. This one works a little bit, but in terms of waste and atom efficiency, it's really not very good. So we kind of shied away from the MCPBA long term and actually found a route that utilized a little bit of acetic acid, a little bit of sulfuric acid, a bit of hydrogen peroxide, and the amberlist, which is kind of an ion exchange resin. And the mix of this allowed us to do quite nicely controlled epoxidations without ring opening. You have to be careful with your hydrogen peroxide solution. You don't have too much water and too much acid in there as well, so you go a stage too far, because you can quite readily ring open that to form the diol, or in this particular case a polyol here. So you have to be a little bit careful with your stoichiometry and your conditions, but relatively gentle ion exchange resin works really well, and you can get a nice, again, relatively clean epoxidized vegetable oil. That itself, again, is not particularly unheard of, because epoxidized vegetable oil, as I already mentioned, is a very large industrial material. We're just trying to do it in a slightly cleaner, more sustainable way. So once we got our epoxidized vegetable oil, we took the really just very basic straight approach. If we got a standard commercial Degiba epoxy resin that was cured by an amine and then just dropped in a certain percentage of bio-based material, what would happen to the resultant polymer that we made? So we added effectively 3 different types of the oil. So the neat oil, so we managed to source the oil before it had been cooked with, after it had been cooked with, and then after we'd cleaned it up as well. And that's the 3 different stages that you see there: neat, purified, and waste. The oil mix in itself, for completeness, was a mixture of palm oil and rapeseed oil, and it was sourced conveniently from the university's library cafe. So we were utilizing a waste material that existed on site that was a problem for us to deal with as well. So again, really ramping up the sustainability credentials of this work. So with this particular oil mix, one of the things that we found pretty much straight away, if we look at the Young's modulus, when you add some vegetable oil based content in, is that across the board, the Young's modulus goes down. Absolutely not a surprise. Again, we're adding effectively a material that is a known plasticizer into a system, and we get a reduction in the modulus. That is absolutely what we'd expect, but we wanted to go through that process just to ensure that it did interact and it cured and it still formed polymers. We weren't necessarily getting significant leaching out of the oil, that the vegetable oil wasn't being polymerized at all, that it was being incorporated into that polymer network. So we went through all of these reaction stages, kind of got this profile along. There was a significant drop at 15% and higher, and what we found was that we were getting crystallization of our polymer, and particularly the vegetable oil polymer was effectively no longer soluble within that epoxy mix. So we were starting to see crystallization, and I think we haven't quite got the images. I haven't put the images in these slides, but you can quite clearly visually see at 15% the sample becomes very opaque very quickly, and that ties in with that drop in modulus as well. So the mechanical properties drop. We get effectively a biphase mixture of two different polymer types, and doesn't really blend very well. So within this particular system, 10% was about as much as we could really push it to. So one of the things that we then thought of was, well, can we then put a very simple additive in that at least returns us to the properties that we once had? And one of the things that we looked at was this product here, which is effectively a milled carbon fiber. And that's a reclaimed carbon fiber that's effectively a powder product, that it can be used as a quite a cheap, sustainable filler. It doesn't have anywhere near the environmental impact of virgin carbon fiber, because it's effectively reclaimed waste material that we're then doing something with. And we did that for the 1 all the way through to 30% of carbon fiber, with the standard Degiba system and our 10% epoxidized waste oil. And we can see again that as we add carbon fiber in a composite structure, we get an increase. Now, we don't ever reach the same levels of Degiba. The Degiba system is always better in terms of its Young's modulus in comparison to the vegetable oil one, but you can see a steady rise, and we're getting well over where we started with. So if we wanted to get back to that product system, or we wanted to at least or exceed it, then the use of the milled carbon fiber was a simple way of just returning those properties and getting them back up. And we can see here that we've got at 38% milled carbon fiber with the 10 weight percent of the epoxidized vegetable oil. In the Degiba, we've now reached a level where we're at about 3 gigapascals of Young's modulus, which is fairly decent for an epoxy resin. We're not out of the realms of what could be considered a fairly decent material, but it's only 10 weight percent. It's still low in terms of its bio-based content. One of the other reasons that we found that was problematic with this is that the amine hardener on our system wasn't particularly good. It didn't really react with these sort of internal epoxy rings. If you had effectively epoxy ring at the terminal there, it would work really well. But here, because of the steric hindrance of these large bulky amine hardeners, we weren't getting a reaction in here. And there's a couple of examples of what these amine hardeners typically are like within the epoxy resin systems. So one of the things that we wanted to look at was whether we could try and change these cross-linkers and hardeners to something that would work better with our vegetable oils, while still maintaining the properties of or maintaining reactivity with the Degiba system as well, ensuring compatibility between the two. So we then looked into starting to optimize the formulation a little bit, and we did a little bit of design of experiments and some statistical analysis to kind of optimize for the best formulation that we could think of. One of the things that we showed that I didn't mention on the previous slide was that effectively the difference between purified, between the waste oil before and after was fairly minimal. So the purification step was well worth putting in there for the consistency of the product. So we just compared the waste oil with purification versus the neat oil. Then we looked at the hardener, and we had two particular anhydrides. We had the phthalic anhydride and the methyl hexahydrophthalic anhydride as two versions of different types of hardener. We varied the molar ratio of the hardener between 0.8 and 1.4, so maybe a slight excess of the oil or a slight excess of the hardener. And then as a catalyst to start this off, we tried two different catalysts as well, one being triethylamine and one being 2-methylamidazole. And the idea here was really just to do a big broad range of experiments to try and find out what was going to be the best way to get the most bio-based content into a polymer without significantly dropping the properties. And so here, again, we did our blend of palm oil and rapeseed oil before, after it had come out of the cooking, purified it with a little bit of aqueous extraction, characterized the number of double bonds now just to know exactly how many we were. That difference there between the neat oil and the waste oil was about 0.7 of a double bond equivalent. So we lost quite a bit of chemical functionality, but there's still quite a lot on average per triglyceride unit, well over two double bonds. So it's still quite a there's enough reactivity there to do something with. We've then got the epoxidation that was controlled. We see a little bit of a drop in the number of epoxy groups because of some of the side reactions that are going on, but again, it's still relatively in line with the oil, so we're not significantly differentiating between the two at this stage. And then we added the hardener, which effectively ring opens and cross links and forms that more traditional epoxy resin that we know. And with that, we added either the triethylamine or the 2-methylamidazole with one of the phthalic anhydride hardeners, and had a curing regime of 140 degrees for 14 hours and then 160 degrees for 2 hours. When you put all of these different variations together, we tried 32 different formulations of varying levels, and that was planned through design of experiments to try and find out exactly what were the dominant effects, what wasn't important, what was important, and what we should really focus on. The first thing we found when we looked at some of these composites was that the thermal stability was pretty good. They were stable up to 290 degrees C, and then when they were starting to go, they were becoming less stable because of any unreacted hardener. So if the hardener wasn't completely reacting, then that was providing a little bit of thermal decomposition, which is again entirely what you would expect. So the higher the hardener molar ratio, the lower the T onset of degradation was, and typically the anhydrides were thermally less thermally stable than the amines. Excuse me. But we effectively have a vegetable oil rich network that had a T onset of about 324 degrees C. An anhydride rich network would give us an onset temperature of about 290. This kind of can be envisaged here. You can start to see that kind of drop with effectively the hardener event first, and you can see the difference between the two derivatives. And there's actually kind of two profiles as part of the degradation as well, which again aligns with the fact that we've got two different, sort of backbones of the polymers in there with our more aromatic de Geber epoxy plus the vegetable oil epoxy material as well. So again, these kind of results indicate, yes, that the polymer is in there. We are seeing a blend of these two materials. We then looked at some DMTA just to kind of understand some of the mechanical properties of this system. The plot here is storage modulus against temperature. We found here that when we had more anhydride, we were getting stiffer material. Again, not a massive surprise because we're increasing effectively the cross-linking density by having more of the hardener present, which you would expect to increase the stiffness of the material. The neat oil materials were slightly higher storage modulus as well. Again, it's got a slightly higher level of initial functionality that it can react with, so you would expect it to, again, have a slightly higher cross-linking density and so on. We then calculated the TG, and this is often one of the big ones that people kind of look towards when they look at epoxies and structural materials. They look at the glass transition temperature, how stiff is it, what sort of operational range can we work in. And we found that the TGs for this system were pretty low. We were going from somewhere around -4 degrees C up to 42 degrees C. Commercial epoxies are probably going to sit around 100, 80, 100, 110 is not unheard of. Certainly much higher than 42 degrees C. And this was when we started to think about, well, these aren't going to be structural applications. We're going to have to do quite a bit of work on the TG in order to get it into that range where structural applications become possible. And we did a lot of work. There's a lot of stuff that was contained within the student's thesis around trying to optimize these TGs to try and push them up to 40 to 50, 60, 70 degrees. But it was ultimately we were unsuccessful in that area, and we expected to be unsuccessful in that area. We tried because we wanted to see if it was possible, but the reality is that we're putting a plasticizing polymer into an epoxy network, and that is going to reduce the TG. And we couldn't really avoid the physics in that situation. That vegetable oil chain, which is quite bendy and flexible, means that it lowers that glass transition temperature. So we knew that we had to kind of think a little bit about the application and where we were headed at that point. We did, however, continue to look at the statistical analysis to see what were the important properties, and it was found out that actually the interactions between all of our different parameters weren't significant based on a sort of a standard significance test. What were the important factors? Was whether the molar ratio was high or not. We got the best mechanical properties at that high molar ratio. It did impact the thermal side, but the mechanical properties were best at that high molar ratio. The catalyst was shown to be significant. The 2-methylamidazole worked much better than the triethylamine. We were getting much more significant increases in properties with that catalyst to start with. Solubility issues, steric hindrance, all electronics all kind of play into this area. And then you've got the oil origin as the last factor. Effectively, if you use neat oil, you were getting a significantly better material than if you used the waste oil. And this was one where we saw the data and we largely threw it out the window because we wanted to use the waste oil. It was like, yes, we know that the neat oil will get us a better one, but what if we use the waste oil? How far can we push it? The other two we kind of optimized and kept in our formulation. We followed through with the 1.4 molar ratio of hardener to epoxy, and we followed through with the use of the 2-methylamidazole as our catalyst. But most of the other things we then kind of left towards it. So then we started looking at making composites out of these materials, and we wanted to see whether they were compatible with a variety of different types of fibers. Again, following a similar sort of curing system, we made a flax fiber reinforced material and a glass fiber reinforced material. Used our optimized polymer mix to see what sort of composite properties we were getting. And we found that that with the change of the fiber type, we were getting some increased levels of bio-based content, which is obviously very good, and with the natural fiber, a lower density, which is great for lightweighting if we're thinking of putting it into automotive applications, but the mechanical properties were lower. And we were getting reduced impact, reduced tensile strengths, and we found that the compatibility of these fibers with the resin wasn't particularly great. So our optimized epoxy resin didn't really seem to be compatible entirely with the resin. We were getting lots of fiber pull out, as you can see here, lots of void content. It didn't look to be a particularly brilliant polymer composite. So we looked at improving some of the fiber surface treatments to see if that would have an effect and improve the property of the composite. So instead of doing nothing to the fiber at all, particularly with the natural fibers, we looked at using sodium hydroxide or stearic acid as kind of two ways of going about it. The idea with the stearic acid as a fiber treatment was to give a surface that would be similar in terms of its properties to the vegetable oil based network. So we've got that kind of long fatty acid chain. Potentially that would give us a little bit more adherence between the two. Whilst we did have not a great result in terms of the tensile modulus, the sodium hydroxide gave it a little bit of an increase. Tensile strength was largely the same, give or take a few percent. It was difficult to really identify whether or not we were having a really significant effect. The stearic acid itself didn't really have anything to do with it. It didn't really help with the mechanical properties. It did help with the water absorption. When coating the fibers with stearic acid did give us a significantly lower water absorption from the fibers. But we notice here that the impact strengths of these materials were all actually pretty good. And it was here where we think, well, actually now, this is where our application has to sit, because we found some materials that have pretty good impact strengths that will adapt well to the different fiber types. Just some SEM images here that kind of show potentially the impact of some of the fiber treatments, that they still weren't particularly great. You get fiber pull out with all of them, and that again largely due that even those fiber treatments couldn't overcome the incompatibilities on that fiber matrix interface between the fibers and the resins. We compared that with the standard, and you can see straight away why our thinking was in this area. Just the standard Degiba, tensile strength was much higher, tensile modulus was much higher, but the impact strength was much lower. And we'd identified materials that had got a really good impact strength, and this was where we should be focusing our mechanical testing on. It shouldn't be around making materials that are the strongest and the stiffest. Actually, energy absorption for us was definitely the way forward. And so we did a number of different formulations, again looking at the resistance to impact, and all of the formulations that we put together with various different glass fibers and flax fibers and different ratios of vegetable oil and hardener, all produced better material. It was effectively the reinforcing fiber. We were getting better stress transfer within the glass fiber biocomposites. We were getting different modes of fracture. And we were also starting to think about whether we were getting different modes of energy transfer through the composite. Were these kind of polymer chains effectively having the ability to move and being a little bit more flexible? Was that helping to absorb some of the extra energy? And this kind of gave us some thoughts that we were having some applications as a Degiba formulation in composite structures. Could we add more and really push it quite high in terms of vegetable oil content if we weren't concerned with necessarily the highest strength and the highest stiffness? Could we get something that would enable us to really absorb quite a significant amount of impact and overcome some of the brittleness that is inherent with epoxy resin formulations? And one of the things that we started to look at was this phenomenon as barely visible impact damage, this sort of BVID. And what you have here is effectively an impact zone where maybe in composites, maybe a tool in a workshop, a hammer or something is dropped onto the composite structure, and you see very little damage on this top surface, but actually you've got cracks and fractures propagating all the way down through the system, and actually maybe some layers down you've actually got complete delamination of the material. And this kind of barely visible impact damage is a real problem in a lot of different composite structures. So if we have a way of kind of mitigating this in some way, this might help us. So again, we took our formulation. This time it was a 30 weight% blend rather than the 10 or the 10 or the 50, just to try and get a nice optimized system. We used again followed through our systems, but this time we looked at it with recycled and virgin carbon fibers just to see how well we could push this. If we had the best type of reinforcement that we could think of, were we really going to start to absorb some of the impact, and would we notice a difference between the Degiba system and our resins? So we made them traditional sort of composite manufacturing with the two different fiber types. Tried to keep them overall, even though we had the different fiber diameters and fiber weights, we had a fairly consistent composite product overall in terms of the amount of material that was in there. And when created these carbon fiber composites, which had 30% bio-based resin in them. And we found, again, we looked at the tensile modulus, the bio-based was lower, and as can be seen here with the virgin carbon fiber, tensile strength, everything with the recycled carbon fiber, lower again as well. So we know that the blend performed lower. We actually got a more ductile sample as well, as would be expected. Virgin carbon, the blended materials gave us the mechanical properties exactly as we would expect in this particular area. But we wanted to evaluate that impact damage, so we developed our own testing kit, which was effectively a 1 kilogram weight being dropped 51 centimeters to give us 5 joules worth of energy, just a little dent on our composite structures. And you can kind of see it is really hard to see. It doesn't matter what size screen you are or on a projector. There is a very small dimp in that composite there that we've induced, and we're looking at that barely visible damage. It's kind of the point of the name, barely visible. We looked at a variety of different sort of imaging techniques, from microscopes and spectroscopic, to try and look at whether we could see different layers and different energy absorptions. We looked at trying to find using sort of digital image correlation to look at some of these events, and we couldn't really see anything with those sorts of imagery. These kind of pictures are all largely inconclusive about what was going on the different layers. That one is an ultrasound, and it doesn't tell us particularly anything. And the ultrasound is what people would traditionally use to kind of diagnose some of these defects and problems. So the ultrasound wouldn't necessarily tell you that there was an issue here. What we actually looked at was the compressive strength, and so what we looked at was the compressive strength before and after impact. So what was that residual compressive strength? And we found that in both cases, the blended materials actually had a higher residual compressive strength after impact, that they were actually able to, effectively repair and kind of improve some of that compression. They were mitigating some of the damage that was caused by that impact and that barely visible impact damage. Effectively, we had a toughened system. We were preventing some of the delamination that was occurring in the brittle Degiba only systems. And that was the conclusion of our work. That's where we got to. We got to a system that we'd optimized and then applied into impact structures and shown that actually that last final point, that we can get a bio-based material that has better compressive strength even after impact, and significantly higher than just having an epoxy standard material. You can do work with surface treatment. We can do some work with the different formulations to promote the amount of bio-based content that we're able to get in there. But fundamentally, where we got to was exactly where we wanted to be, in the sense that we'd taken a waste oil, we'd valorized it, added it into a commercial system, reduced the amount of fossil fuel and fossil reliance of that composite to make something that was better than where we were previously. And that for us was a really significant result. I'd like to thank Felipe, whose PhD this was largely based on. He's now back in Brazil, but the CMPQ was his funding organization. Danny and Peter did some of the work as well in various other things. Kerry is supported this work consistently throughout and was Felipe's other PhD supervisor. So they're the people who did the work along with myself, and I'd like to thank them. Certainly I'd like CMPQ for funding, but most of all I'd like to thank you all for listening, and again thank you for the invitation.
Thank you so much, Dr. Coles. So let's begin with the questions. You can send them through the chat. Thank you very much, guys. This one is from Omar Rogelio Gomez. Thank you very much, Dr. Stuart, for introducing us to your stunning work. The optimization of the formulation was successful. With these results, there is any approach with the industry for pilot production?
For the pilot production of the resin, absolutely. All of the processes that we've tried to use throughout this work have been industry standard processes. So the biodiesel is how you clean up oil to make biodiesel, and that's what you would find within, the UK now has 7-8% biodiesel in all of its petrol pumps. So biodiesel is quite a large scale thing. The epoxidation is done on a large scale with the vegetable oils. We can do all of these steps. It's about finding the application that works, because the infrastructure to do everything else is already there.
Yeah, it's also there in the WMG. You have these large machines that you can do the prototypes.
Yeah,
but then you have to think in that product, really, a specific product.
And that's fundamentally what we're about as a department. We're an applied research department. We're looking to take work and translate it into the commercial world by finding applications where we can have success in. And this is a great example of that, because we've made a material where it does have potential to be applied in industry in certain sort of sectors where impact is of prime concern. You're absolutely right. The scale of the machines, and I haven't got the pictures or the slides to show, but all of our machines are kind of industrial scale. We are prototyping and test kit and everything is done with that kind of application in mind.
So Gerardo Jose Bolivar, thank you very much for your talk. When working with waste vegetable oil, what maximum percentage of clean triglycerides is possible to obtain?
We never looked at isolating the percent. We never looked at isolating the sort of like the percentage of clean triglycerides. We characterized the drop that we were getting in functionality that was approximately 25%, 20 to 25% in the drop of sort of double bond content. But we never looked at isolating the clean triglyceride, and that was purely for sort of long-term thinking about the economics of the process. That if you started to having to purify the triglycerides and return it back, you were going to be adding significantly higher cost into that process and extra steps. And what we wanted to try and do was actually just use the material with as minimal amount of processing as we could possibly get away with. So we never isolated a clean triglyceride. So exactly how much you could isolate, I don't know. But I know we were we were experiencing a reduction of functionality of about 20 to 25%. So therefore there must be a similar reduction in sort of clean content, as it were.
So thinking about the sewer system and the Fatberg, this is a new term for me. I didn't know it. What about another cities? You were thinking about London, maybe. In Coventry, do you have the same problem?
Yeah, this is a problem all over the UK with the UK sewer system. Devon and London are about as, in terms of the UK system. Devon is quite a rural community. There's not that many large cities. I mean, the largest one, you've got sort of Exeter and then a couple of others on the coast, but it's quite dispersed. It's quite remote. It's not the huge population density that you have in London. So in terms of the demographics and the geographics, they are very different areas. But this isn't just limited to the UK either. Certainly, there's this issue in Spain, in sort of Central Europe as well. It's quite a well-known problem for water companies in this area that are trying to deal with. I think in part it relates to climate, because the temperatures that the sewer system exists at are obviously much lower here than potentially over in Mexico, as an example. And, if your average ambient temperature in a sewer is 25, 30 degrees as opposed to 0 to 10, that makes a difference in the sort of the solubility and the liquidity of that oil. So maybe you don't observe it in that way that we do here.
Yeah. So you were thinking with the Fatberg, you began with that, but then you use palm and rapeseed oil. Why? That's
We
the main.
we used that mix because that was the mix that was being used in our kitchen on campus.
Okay,
So we
yeah,
wanted
I
to
remember
get
that. Yeah, yeah, the restaurant, right?
yeah.
Yeah.
We could have bought any vegetable oil. It didn't matter. Like fundamentally, if we're using a waste, we could have gone to any chip shop. We could have gone to a McDonald's or a Burger King or plenty of other places to get the oil. But we wanted to get something that was obviously close and related to campus. So we went to the cafe in the library, and they do lots of deep frying there. And
you changed it?
No, we didn't change it. So the oil, we asked, the chef was very kind in providing us with. I mean, from a resource perspective, anyone on the call who knows about sort of resources and chemistry, if you get like 10 or 20 grams of material, often thinking this is brilliant, the chef was able to supply us with 25 liters of both the neat oil and the waste oil. So we had more than enough material that we could possibly do with. But we asked him, he said, we just want whatever oil you cook with, and we want the waste version of it. And it was just that the oil that the university bought was a mixture of 3 parts rapeseed to 1 part palm oil. That's what was used in the kitchen. So we didn't start off with saying we're going to go for this mix. It was just, this is what they use, so that's what we're going to deal with. And again, that's kind of a more reality. It's a real situation, because if you're a wastewater treatment company dealing with fat, you don't get to choose what comes down the sewers.
Yeah.
You deal with what your suppliers, quote unquote, are giving you. And so here is what we did as well. We said, well, this is the material we've got on campus. Let's try and solve that.
So then you have the challenge of the oxidizing the vegetable oil, no? So you have to have a unsaturated system.
Yeah.
So you can make the reaction. Then I think about, because we experienced that in Alfonso's thesis, and I told you before we began that the main problem is the position of that epoxy groups in the vegetable oil, no, compared to DG. DGBA has in the, it's easy to get to the epoxy group, but then I don't know if you have considered also a different kind of oil that have more possibilities to have more epoxy groups.
We did think about potentially looking at maybe doing uh, a little bit of catalysis on the double bonds to try and make them effectively terminal rather than
Hmm.
in the middle of a chain,
Yeah.
and doing some fairly sort of standard catalysis there to just kind of try and open them up a little bit. But we went back to that same thinking of before, that we were adding extra steps in and trying to complicate it where maybe there was another solution, and that's why we went down the route of looking at the different hardeners. So instead of using the amine based ones, we looked at the anhydride ones, and they worked, they worked pretty well in terms of getting the sort of the cross-linking density and the material quality up there. We weren't seeing what we would if those hardeners weren't working with the polymers, certainly from a physical perspective, you get a kind of greasy material because your polymer would start to leach out over time because it isn't entrained in that polymer network. And we weren't observing any of that kind of thing. So we really were quite confident that the anhydride was doing what we'd hoped it would do. But you're
Yeah.
absolutely right. It's a difficult material to work with. We kind of started this. We did a load of work on polyurethane systems years back, and in that system we were absolutely hitting it with tungsten catalysts and volumes of hydrogen peroxide and really saturating that system using oil, water, and everything to try and get it all the way through. But that was a horribly wasteful approach with liters of water wasted and tungsten as a material. So it wasn't a good solution.
Yeah, and that's the thing that you are working with right now, no? Sustainable processes, not
Yeah.
only the to achieve good properties for this material.
Mm.
So you have a process that is more green, green like
Yeah.
green chemistry, no? So
Which
the last thing I want to ask you is about the carbon fiber. You used recycled and virgin carbon
Mhm.
fiber in the last system.
Yeah.
Um, then I think maybe the main difference between the two materials is that the one is woven and the other one is not.
Yes.
And I,
Yeah, that
maybe
would in that system, that's the main functional difference between the two of them, and that obviously gives you reduced properties. So we were never comparing what's the difference between virgin and recycled carbon fiber, because we know that there's a
yeah.
there's a difference there. So we were always comparing, well, what effect does our oil have if it's this reinforcement, and what effect does our oil have if it's this reinforcement? I mean, I like recycled carbon fiber as a feedstock because uh, it still has really good properties, even in the non-woven form, and certainly for a lot of standard engineering applications, you can do enough with carbon fiber that it provides you with a really robust composite for application.
Then they use it as a filler, right? Not a reinforcement fiber.
Yeah,
And
certainly the first applications for recycled carbon fiber came off sort of like milled, where it was just being ground up, and that's that first powder that we showed in one of the earlier bits of the work that was in the slides. That the you just chuck that in as a reinforcement, but now they're getting a little bit more. The recycling process effectively pyrolyzes the resin, so you just
mhm.
remove the resin off, leave yourself with the fiber, which is then kind of almost like chopped into short fibers, and then you kind of you can rewind it and get long fibers back again, or you can keep it in the short form. We've done a lot of work with the short fibers in sort of thermoplastic processing, so putting maybe sort of an average length of about a 6 mil recycled carbon fiber in polypropylene, polyamide systems, and looking at whether how good they are as a structural reinforcement.
And maybe in this kind of processing, the roto molding is a good choice to have this carbon fiber, no? Because small, it's dust really, so you
Yeah.
can mix it
Any
the
any
particle
sort
size that you use in roto molding.
Yeah, any sort of molding process where you can keep it enclosed is really important,
Yeah,
because the milled carbon fiber particularly is really dusty, and if it
yeah,
gets into the atmosphere, you've got problems with operator health and safety because of the particulates in the atmosphere, but you've also got problems because the carbon fiber is conductive, mill carbon fiber, so you get like electrical shorts and all kinds of other things. So you want to keep it enclosed as best you can. So even extrusion isn't brilliant because you've got to load it in through a hopper. So
Yeah.
rotor molding is lovely for it.
Okay. We can consider that for a new project.
Yeah,
Dr.
definitely.
Stuart calls. So thank you very much for being here. I know it's kind of late there in the UK, but it's we are very. I thank you very much because of that, and we want to work with you again. So maybe this could be a good chance to get each other, the catch up talk that we needed to begin with another project. So thank you so much, Dr.
No problems.
Coates.
Delighted to be invited, and you're absolutely right. It'd be great to continue the chat very soon.
Thank you. Bueno, voy a cerrar la plática en español. Ahorita le digo a Stuart qué fue lo que dije. Les agradezco mucho que hubieran estado acá, que estén a tiempo, eso siempre es importante. Y en la página web del doctorado en Ciencias e Ingeniería Química dejé un vínculo en el nombre de la plática con las diapositivas que utilizó el doctor Coates en la presentación del día de hoy. Así que les mando un cordial saludo, que tengan un buen fin de semana. Nos vemos después.